All right, and we are live. Well, welcome everyone to the first lecture of hot distributed summer. So today I'm really glad I have my friend and colleague and co-host Matei, who's going to be here with us. And the main speaker for today is going to be Jeff Hammond, who's a principal engineer at NVIDIA, and he's going to be talking to us, hopefully giving us a tour of all the different kinds of programming models in NVIDIA. So thank you, Vikram, for making the introduction, and Jeff, please take it from here.
Thanks. So I said I'd introduce myself a little bit. So I am part of the Nickel NVSHMEM team at NVIDIA, and obviously I'm talking on behalf of the work of 45 other people. I'm not a developer of Nickel and NVSHMEM at this point. I'm just trying to help the team get in the right direction and then explain this stuff. And what I've done most of the year is write code and try to come up with the ideas that need to be out there and learn things. But I've been doing HPC communication stuff for about 15 years. I worked on Blue Gene back in the day, and I've been a part of the MPI forums for 15 years now, and have contributed to the last 3 releases of that standard. And so when I say bad things about MPI, I do it out of love. MPI is fantastic, but it does have some shortcomings, and those shortcomings will be part of this talk and part of the history of Nickel. So I'm going to do my best to teach everybody what I've learned and what I think is interesting. There's many hours on this. Obviously, GPU Mode has covered this topic before, and they will cover it again in the future. And there's some content online that I'll refer to, GTC talks, etc. So if you're watching this video on record, you can check out those links if you want to stop in the middle and get more background from my colleagues. If it helps, but hopefully this will be self-contained. So the questions I'm going to try to answer today. So we have 2 communications libraries, not one. And folks may wonder, well, why do you have 2? What's different about them? What do I need to know? How do I choose one or the other? And I'll try to answer that. People who saw Marcus's talk 2 weeks ago, I remember there was one comment I thought I saw that was something about, well, why use Nickel if MPI does the same thing? It looks fine. And, so they're similar, and there's a reason they're similar. And I'll try to explain why Nickel exists and why it wasn't sufficient to use MPI in the context that Nickel gets used. I'm going to show a bunch of experiments. I wrote a bunch of code. I don't teach code that I didn't write myself and didn't debug and painfully learn. And I'm going to show the code that I wrote, which isn't perfect. I didn't finish every possible example that I thought I could write, but I got a whole bunch of examples that I think are interesting. And all of that stuff is on GitHub. I merged the pull request this morning, so you can check it out. And if the code is confusing, you can hit me up on GitHub or these guys' Discord channel and ask for help. And then lastly, I want to talk about forward-looking strategies for optimizing communication. This is inspired by what the AI community has done recently with NVSHMEM, which is really interesting because NVSHMEM wasn't created for AI users, but it has turned out to be really, really interesting for a couple scenarios, and I'll explain what those scenarios are and why NVSHMEM got used, and then what does that have to do with Nickel? That'll be at the end. So I'm going to give an overview, then I'm going to give a historical context. This is a thing I think hasn't really been said before. A lot of people who are in the AI world just know that Nickel is awesome. So they talk about Nickel, and our documentation refers to MPI because there's one of the lead developer of Nickel is himself an expert in MPI as well. But it's not, and there's a historical tradition sort of inherited from MPI into Nickel, but I don't think people appreciate that. And there's also a historical tradition for why NVSHMEM is the way it is. And this gives us a context for reasoning about their differences. Talk a little bit about GPU and MPI issues. Then I'll show my experimental stuff. I'll start with explaining it in terms of MPI and SHMEM. I know that maybe those 2 things are less familiar to the AI folks who just learn Nickel. Or something else from the cloud world. But I think it's important to start there. If you're an HPC person, that might make you happy. I'll show the experiments. I wrote some benchmarks with collectives and point-to-point and one-sided and load store on my DGX H100. and I measure it, and you can see the differences, and we can learn from the performance of these experiments at small scale, and then reason about how they scale, and then I'll wrap things up. So these are short overviews, 1 or 2, 3 slides each. There are hour-long talks at GTC on these, so please go check those out. I'm not going to try to be complete here, but I'll try to get the big picture. So NCCL is designed to address the major patterns of AI training and now much more inference as well. So, in the beginning, it was all about all reduce and the ring algorithm and coming up with multi-GPU solutions at small scale. But that was 10 years ago. So NCCL's just turned 10, I think, about a month ago. And it has evolved a great deal. So it's got support for all the different collective patterns. You can use it for all the different types of AI parallelism, data parallelism, tensor parallelism, pipeline parallelism, and expert parallelism are all captured. And of course, we also, it's our job to support all the systems. So you can use it on your multi-GPU workstation. You can use it on your DGX box, your NVLink domain, however big that is, which of course, folks know is a lot bigger than 8 now. And you can use it on very, very large systems. So people run AI training with NCCL on thousands of GPUs on a regular basis. And NCCL has evolved to a great deal to support those use cases. And so Sylvain, who's the lead developer of NCCL, gives a GTC talk every year to explain these things, and you should check out his talk, and he'll describe in much more detail these patterns. But today, I'm only going to talk about the all-to-all pattern. I like it, and also it's related to expert parallelism, which I think everybody knows is a pretty big deal in the AI world, and I'll try to capture a little bit of where that's going and what you can do to write code for it if you're going to write your own. Obviously, the NCCL ecosystem is quite large. It's basically everywhere. It's in all the frameworks. Most people, I think, probably use NCCL because they're using PyTorch distributed. But it's obviously the advantage of the NCCL ecosystem is, it's all the frameworks, all the models, and all the clouds pretty much are going to run NCCL. And therefore, it's a really good thing to learn, because you can use it everywhere. It's not going to be some niche thing that only runs on one network or whatever. Obviously, we support Ethernet, InfiniBand, and AWS has a support for their EFA network in a plugin. And HP and Cray Slingshot also has a similar plugin capability. So you can use it essentially everywhere. So NVSHMEM is a different model. If you understand HPC, the history of HPC, this is more comfortable for you. But NVSHMEM represents a partitioned global address space model. And the global address space part means that you can think of indexing using pointers into all the memory, all the GPU memory, not just yours, but all the other GPU's memory. And the partitions implies that you can't think of it just like a shared memory domain. You do have to think about the fact that there are different address spaces that are combined together to form this model. And then the symmetric heap is this idea of allocating memory within this combined address space of all the GPUs, and then you can communicate. You can send data from your private space to remote data, or you can do a collective operation across the symmetric memory in all the GPUs. And I'll explain more later why there are some interesting advantages to this model. So there's a GTC talk from a couple of years ago. This is the one Google found for me. Maybe there's a more recent one, but this is a good one by Akil, who leads the NVSHMEM team, and Jim Dinan, who used to, talking about the whole history of it and all the features. I will also note that at Hot Eye in a week or two, my coworkers are going to give a tutorial on NCCL and NVSHMEM, and I think it's free. So if you're into this stuff, I know they have a great tutorial plan, and you can check it out. So the really important thing to understand with NVSHMEM APIs, so the historical SHMEM API, you'd have put, which you look at this function signature, it's basically memcopy, except it's got this PE index. And that just says, which GPU are you going to copy or to? And that means you can do basically memcopy to all the GPU's memory. But there's also more. Obviously, like Nickel, there's the stream APIs, and that's really important to integrate with the CUDA model to be able to enqueue this stuff and not have to block. But the thing that makes NVSHMEM really, really special, and the reason why it has been unique in its role in the GPU ecosystem, and the reason why it's used in some of these MOE models, is it is the only model that supports device-initiated communication. So if you want to do a CUDA kernel and actually go from that CUDA kernel without returning and going back to the host, but straight out of that kernel to send data either to the NVLink domain, you can do that, or you can even send it across the network. And you can do this at the thread level with the putmem, or you can do this at the block level with block and putmem across with a warp as well. And the reason the block and warp exist is folks probably know at this point that GPU memory access needs to be appropriately coordinated and coalesced. And if you want the threads to cooperate on one of these operations, you can do it at the warp or the block level, call it cooperatively across a group of threads, and they will behave like basically like a multi-threaded memcopy. So they'll be appropriately synchronized to work together in the way that they need to generate efficient memory access. So this is just the putmem APIs. Obviously, there's a bunch more APIs. There's get, and there's other operations. The other thing you can do is you can do device-initiated collectives, and you have to be very careful. You have to use cooperative group launch because obviously collectives synchronize, and so you need to have the forward progress guarantee from a cooperative group launch. But if you do that appropriately, then you can actually have, say, an all reduce or a barrier or whatever you want inside of a CUDA kernel. So all the GPUs can be running CUDA kernels persistently and doing communication and synchronization between them without having to return back to the host. And, if you really care about latency, this is a big deal because, CUDA kernel launch has been optimized like crazy. It's really, really fast, but it's still more than a microsecond. And if you want to be doing really fine-grained things, interleaving communication and computation, as I think folks really want to do, this is the way to do it. And so NVSHMEM is solving this problem uniquely today. It won't be unique by the end of the year, but I'll get back to that later. So NVSHMEM has historically had C APIs, but one of the things my coworkers have built this year that's pretty neat is they built a Python-based front end for the NVSHMEM APIs. That was in part because what we noticed is that the C APIs were getting wrapped in Python by AI users and used in their Python-based AI frameworks. And it seemed to make sense if we could build the Python APIs and ship them, then they could be systematic and complete. And we wouldn't have to count on our users writing their own Python wrappers everywhere they went. And we've seen a whole bunch of different interesting use cases. So folks are doing expert parallelism and MOE, DeepSeek and Perplexity are both doing that. Obviously, they've both been public in describing what they do. DeepSeek's wrote some great papers, and Perplexity's wrote some great blogs, which I'll cite later. Perplexity published a benchmark where you can read how they do this and what it looks like. You can put it in Docker and run it yourself and learn from it. You can also do, fused compute and communication kernels. Obviously, that's the whole point of having device-initiated communication. There's also a lot of support for latency optimizations and for 0SM. So obviously, if you're really wanting to be efficient with your AI compute and your communication, one of the best ways to do that is, don't use any SMs for communication if you can get away with it. And so NVSHMEM can use the copy engine and do collectives that way. And that obviously doesn't take away any SM resources for moving data around. And then, of course, consistent with what it is and its history, NVSHMEM has one-sided communication everywhere, whether it's on the GPU or on the host. And I'm going to talk about one-sided and two-sided in just a second. So there's a lot of ecosystem adoption here, maybe not as much as Nickel, but certainly there's support in the major frameworks, including PyTorch, if you want to check this stuff out. I will also say that we at NVIDIA use both NCCL and NVSHMEM internally in some of our libraries, both for AI and HPC. So if you're into the HPC side of things and you do 3D fast Fourier transforms in, say, fluid dynamics or molecular dynamics, CUFFT multiprocess is based on NVSHMEM and gets ridiculous performance compared to sort of traditional host-oriented solutions because of that. All right, I'll pause here in case the hosts want to interrupt me with any questions. Otherwise, I'll continue. Okay, so I'm going to give a brief history. So the world that we see today with AI comms is heavily influenced by the 1990s. Which for me I was not doing a lot of computer programming in the 90s outside of a TI-82. But there was a lot of interesting stuff going on. So the two paradigms of HPC communication, one is MPI. So MPI is a lot more than just send, receive, and collectives now, but in those days it was basically send, receive, and collectives. And it was, message passing is synonymous with two-sided communication, send, receive. We use all these terms interchangeably. The MPI forum started in 1993, and they didn't come up with any new ideas when they were doing this. What they did is they took about 10 different similar APIs that had been built and said, well, what's the right way to standardize this? Because everybody, including the vendors, wanted to not have to keep building one-off APIs for every new platform. The vendors hated the lack of portability to their competitors, and the users hated writing 10 different versions of the same darn thing, especially since, back in the day, they might have been writing in Fortran. It was a little bit more annoying to do this then. The other thing is that the design of MPI with send receive is essentially universally portable. I'm not aware of any environment, any reasonable computing environment that doesn't support it, because you can map it onto something like POSIX sockets, and that's pretty much going to be everywhere. So even if you don't have a fancy supercomputer, MPI will work and do a reasonable job. Token ring Ethernet, whatever it is, you can do it. And so the power of MPI has been that it made absolute portability one of the primary goals, and so it got used everywhere because everybody knew they could use it everywhere. Some of the interesting downsides that we look at in MPI are because MPI was designed when CPUs were relatively fast compared to most networks, and so there were some things that were like, oh yeah, that might cost 100 cycles, but who cares, because we've got a whole lot of time to do the CPU compared to the network. That's less true now. And so some of the things that are in MPI, some of the generality is annoying. And it's particularly annoying on a GPU where the single threaded performance is not the same as a CPU. And this is neither a good nor a bad thing. It's just an important thing to understand. Two-sided communication combines synchronization and data movement. So what this means is, if you're going to move data from one place to another and you need to know when, in terms of programmatic ordering, it's going to happen, you will know. You will say, at this point of the program, send will happen, receive will happen, and you'll know that when the send and the receive happen, that creates some sort of ordering in the program in terms of execution, not just that the data moved at that point. And that's in stark contrast to what we'll see with one-sided, which is also known as remote memory access, or RMA, in the MPI world, and it is really exemplified by the HMEM model. So HMEM was created for the T3D. I don't know every single thing in the Cray T3D that was totally original, but it was an absolute revolutionary system. First torus network, as far as I know, and probably the first sort of distributed load store network. Basically, you had I think it was a DEC Alpha CPU or something like that, and the memory controller could inject into the network, and this meant that you could do a store to remote memory in 90 nanoseconds. And today you'd be happy if you could do that in 900 nanoseconds, just because systems are bigger and hairier. But this meant that the system was somewhat globally addressable, and HMEM was a really great model for that hardware. The legacy of SHMEM is that it's turned in and been standardized as OpenSHMEM, which really captures essentially all of the historical evolution of SHMEM from 1993, 94. And it is standardized so that it works everywhere. But it's interesting philosophically. It says in the OpenSHMEM standard, please don't do a bad implementation. They want people to use it in a way that assumes forward progress in the network, and usually a hardware implementation of that. Because when you assume that, you write code slightly differently, and it makes it more portable if it's sort of either good or doesn't work, as opposed to being good or bad. Because then programmers start programming for the bad cases. So that's sort of a philosophical difference. But I think one of the elements of this is that the design of OpenSHMEM is designed to be very lean from the perspective of what it takes to implement. It assumes either shared memory load store or non-coherent and RDMA. But it doesn't try to assume much more than that. So if you have a lean RDMA network, you should be able to implement it properly. And this actually matters for when we go to look at how we do GPU communication. So one-sided communication decouples synchronization and data movement. What that means is you can write to data and have no idea what the state of execution is on the other side. So you better, if you need to know that you can't write into a memory location until something has happened on the remote side, you need to synchronize yourself. You have complete control, but now you have to do the work. So this can add complexity to programs and make it harder to reason about and debug. On the other hand, that once you get control of this, you can amortize and remove a lot of synchronization and just get data movement going, which can lead to high performance. And we'll see a little bit of that here. And you can read the links in the footnotes if you want to know more. So Send-Recv. So this is the essential part of Send-Recv is that there are two halves. You think of it like a puzzle or a lock and a key, that the sender knows some metadata, the size and the data type and the tag, which is just a random index to get things to match up, and then where it's sending to. But only it knows the input buffer address. And then the receiver knows the output buffer address, and it'll know the same metadata. But there's something called a matching protocol that causes the Send-Recv to get lined up so that the input data can be written to the output data. And regardless of what happens under the hood, there is an implicit or explicit handshake that's going to happen to wire these two things together. So there's a natural synchronization flow between the send and the receive. Somewhere in the wire, this thing is going to line up. So one of the ways this looks like is the sender will send something over to the receiver, and the receiver will, for example, register the memory that it's going to have written to with the network. And then, if this is IB, the memory registration key, and it'll send back that information as a permission to send. And the sender will say, okay, well, now I know I can write into this data. So it'll RDMA write into the receive target buffer. This is one of many protocols. You can read a great paper by a friend of mine from the NVPitch group from many years ago on all the different ways to optimize Send-Recv with RDMA on IB to see different versions of this protocol. But this is just one of the examples. And if you think about this from the perspective of what we're going to do on a GPU, having this extra rendezvous thing go on can be kind of complicated. And sometimes we might just want to go straight to the network with the data. So one-sided communication, you can think of just cutting the Send-Recv in half. So instead of a send and a receive, you now just have a put and nothing. So the receiver does nothing. The put knows the input buffer and the output buffer address or the offset, and it just writes across into the target location. It knows what it's going to do. It knows where it's going. It has that information, and it just does it. There is some setup involved, and I'll show that in just a second. So there's this preliminary setup operation that makes this possible. But that setup can happen once somewhere else in your program, in your puts. When you get to it, if they're on the critical path, all you do is send the data. Get is the opposite of that. It does, obviously, it pulls. So you do read from wherever the remote memory location is, and you read it unconditionally. You don't know what the other side is doing. You're going to read from its data because you have enough information to do that. Again, because permission was already granted in this setup process, which, in SHMEM, it's a malloc. So there's a special malloc call that's a collective operation that says, this is memory that everybody can read and write to when I give it to you. And so that does, among other things, the memory registration. There's a whole bunch of setup that happens there. It's not a cheap operation, but the beautiful thing is you do it once, and now you have this big slab of memory, which is globally indexable to the whole system. And then you can, fire off as many puts as you want, and the data will just go without any additional work. So this matters, and it's always mattered, but it matters more now, and especially on GPUs. So if your send and your receive don't line up, the processors may idle. Sometimes things happen in the background. It depends on the hardware, it depends on the system software stack. But it is possible, if you're not lined up, that you'll wait. So if you have a blocking send and the receive hasn't been posted, you will wait until the receive is posted before something comes back. In the same manner, if you post a receive and the send isn't ready yet, the receive will just sit there and wait. If you turn this into non-blocking, then you have to worry about background progress. Obviously, we don't want these things, any of these serialization bottlenecks, to get in the way of GPU compute. You don't want to have a GPU idling while the host is waiting for something to happen with the network or whatever. And even if we can put this on the GPU, you don't want to be synchronizing blocks and threads just to wait around on doing some metadata exchange or whatever. You want to be moving data as fast as possible. The other thing is we want to pull out everything that isn't data transmission, because the data transmission is usually something we can offload to specialized hardware. Obviously, InfiniBand and RDMA in the networking space, and then GPUs have copy engines. And these are really efficient ways to offload data to special widgets, keep it out of the way of the compute engines. There are ways to offload some of the message matching logic, but it tends to be a lot more difficult. And so we'd really like to get that out of the way if we can. And the big motivation here is, even if it's possible to make all the send receive stuff run really nicely, there's just no reason to do it if you don't need the synchronization primitive that's implied there, because in essentially all AI and HPC communication patterns, there's a persistence. So you're going to do something iteratively, whether it's iteratively training or looping over a tensor operation or whatever it is. If you're going to do communication a million times, why would you want to do the send receive rendezvous a million times? Just do it once up front, set everything up, and go. So
sorry, Jeff, do you mind if
yeah.
we do questions?
Yes, please.
I already had like 6, but maybe before I get greedy, Matej, do you want to go first?
Yeah, I just have one that was written in the chat before, and it's regarding like the first slides, and it's about the difference between data center GPUs and consumer graphics, right?
Yes.
So the chatter was asking about the division between communication protocols and stuff in between those two. Mainly that some algorithms work on data center GPUs, but do not work on consumer GPUs. And like, is there any process to get rid of this division and so on?
Well, yeah. So the first thing is because Nickel's having its 10th birthday this right now, we've been talking about history a lot. So the original version of Nickel actually went through and just optimized for PCI peer-to-peer between GPUs in a box, and we still support that. So even if you have two GeForces 4090s or whatever in a box, Nickel will work. Obviously the NVLink is a data center thing, and that does change significantly the performance. And I don't know off the top of my head all the protocol dependencies. I actually don't have two 4090s at home. So I mostly look at NVLink. So I can't tell you internally what Nickel turns off if it doesn't see NVLink. But I'm not aware of any features that don't work. It's just how Nickel does protocol selection.
Yeah, it was mostly related to not like features being turned off, but then like algorithms not working properly. Like the question was regarding async TP, which is kind of communication heavy, and you kind of can't do it on consumer graphics.
Yeah. Yeah. And I guess at some level there, even if we could do it, how well would it work if you're at PCIe Gen 5 versus, which is on a good day 50 gigs and NVLink is 900s or 450, I guess, if you do unidirectional. So yeah, I'd love to hear more about it in Discord if you can post the details, because I haven't seen much of that topic.
All right, I'm gonna speed run through a couple more questions. So Jeff, since on the topic of history, like you mentioned, like quite a lot that like MPI, like one of the reasons why it like sort of conquered the world for so long was primarily because of its portability and backwards compatibility. Were there sort of like any things that you think they really got right in those early days that are underappreciated?
Yeah, well, I did a whole lot of work on MPI 3, 4, and 5, and I think we've gotten a lot of things right over the years. So one of the things, and Nickel looks a lot like MPI because we appreciate MPI. So we understand that the design of the collectives, having collectives as a first-class object is really important, because, if you think about all reduce, if you want to do an 8-byte all reduce, you do a very, very different algorithm than you do if you want to do a 1 gigabyte all reduce. And what you want is for a user to say, here's an all reduce, here's a byte size, and then the implementation will go figure it out. You do not want some user deciding whether they should do a tree or a ring or a multi-ring or any of that business. So exposing all of that logic as first-class primitives to the user was incredibly important. Send-Recv is a really good way to write a lot of algorithms. I know I just bashed on Send-Recv a whole lot because calling Send-Recv from a GPU would be a bad idea. But the concept and the host-initiated version of it is a really good way to, very general purpose way to write code, very safe. Rusty Lusk, who had a huge influence on MPI for its entire history, used to talk to me about performance transparency, that when you write an MPI program, it's really easy to look at the code and say, this thing is going to be fast, this is going to be slow, and this is what I need to do to fix it. And in contrast, some of the stuff that makes everything look like a single memory space can sometimes give people bad ideas, and they can start doing 8-byte accesses across a network that's 10 meters long, and that can be a bad idea. So there's a lot of good stuff in MPI. The thing that I'm going to talk about on the next slide is just that it has too many goodies in it for GPU execution. But the other one, right, is consistency. MPI has, with maybe one or two exceptions I can count, that no one cared about. We've never broken backwards compatibility. And actually the thing I just spent 3.5 years on was we now have a standard ABI, which will be a big deal. So we're doing a lot of things to make the usability high. So
speaking of the programmability of these things, like I kind of didn't fully understand like what does HMEM do very well, in the sense that like when you were pitching NVSHMEM, you were saying something along the lines of like you can initiate like device side, it comes directly. Obviously for HMEM that's not the case because everything is a CPU. So what were the applications where HMEM really shone? Where HMEM did a really good job? Sorry,
yeah. Well, HMEM doesn't have a historic up until if you don't count NVSHMEM and the AI use case, HMEM is known for having a pretty small but very, very serious user community in a particular branch of the United States government. And they write very, very large scale unstructured data analytics applications. And the operative word there is the unstructured. So, Marcus gave a fantastic tutorial on Stencil, which is structured, right? When you have a physics code, you do a domain decomposition and you say, okay, well, I've got Cartesian physics and I do X, Y, and Z, and I can pair all these things up and I can build this, beautiful graph of communication and map it onto MPI, and MPI will just do a great job with it. And so historically, MPI has done a really good job with structured programs. The unstructured stuff, you could do it, but you sometimes have to resort to patterns that are not necessarily the most efficient. And that most efficiency matters when you're doing really large scale applications. And so a good example of this is if you're going to do sorting on a supercomputer, and you're going to, first you do, you do a local sort, and then you do a histogram, and you say, okay, some of these keys are going to go to different buckets, and you know where these buckets are. So you start flinging these buckets out to all the different remote nodes. But the thing is, only the initiator knows how much data it's going to send to a given remote process, because only it knows what the keys are, and it sorted them, and it can see that histogram and say, okay, here you go. And so you can't really write a nice, happy code where that information is known where it needs to be known in advance. And you can basically do a rendezvous. So if you want to do Send-Recv, you have to either do polling and say, well, I'll accept whatever data comes in, or you have to do, well, I'm going to look for a specific thing, and if I see it, then I'll wait for it and go get it. And so you have all these ping pongs going back and forth to exchange. Whereas if you do it with SHMEM, you basically just say, well, I've got, 1 terabyte worth of distributed memory aggregated together for my target space, and I can just spam the whole system, put everything where it needs to go in chunks, and not wait at all. And actually, what I just described, right, is actually the reason NVSHMEM is used in MOE, because what's happening is you have this routing function, and the router knows where these keys are going to, or whatever they're called, tokens are going to go, but the expert that's getting hit with them doesn't know which data is coming where and where it's coming from. So what you do is you just write it over there, and then it'll go look and see what's in the mailbox and go start working on it. So it's the unstructured part of SHMEM that has been killer for many, many years. It's just that historically, the MPI was used primarily in the physics domain for a long time, where it was better. But I think they're good at both. But you have to. It's sort of like, which is a more natural thing. If you really only care about one app, you might pick one or the other.
So, okay, I think we might need to keep going. I have a lot more questions, and I saw all the questions in chat, so we'll just get back to them at the end of.
Okay.
So please be patient with us, folks. Thank you.
No problem. All right. So MPI versus nickel. So Marcus talked about, and I think everybody has seen it before, the stream support. And he gave a good example of, well, if you want to do an MPI send after a CUDA kernel, you have to synchronize, and then you do send. And obviously, nickel, you could just send because it goes on the stream, and the CUDA runtime sorts it out. And MPI 6 may solve this, but we don't have it yet. The other things that MPI allows that people don't think about as much, unless you're an MPI nerd, you can do underflow in MPI. So you can have the receive be 1 gigabyte and the send can be 8 bytes. And, that can matter. It means you can't do protocol selection independently. Only the sender can do protocol selection. So the receiver has to get some information, and this adds a little extra logic. MPI data types allow you to do basically anything. You can have structs of structs of structs, 18 level deep, non-contiguous, all sorts of weird stuff. And the data type engine is really, really powerful, really beautiful and elegant, but not actually something I think is a good idea to run on a GPU. You don't want to have that type of generality to do GPU processing. You might be able to do it, but it's not a good idea. MPI supports tags, which isn't a huge deal, but it means that you have to distinguish messages based upon some ID. You can't just say, well, I post a receive, here's a send, I can line them up. The thing that everyone hates, unless you have to use it, or the implementers all hate, but the users all know is sometimes critical, is wildcards. And what this means is if you didn't have wildcards, you could post, you could basically separate the message matching logic into bins. And you could say, well, I know that I only have to look over here to match a message. I know that this message won't match with me, so I can do this in parallel. But the any source is essentially a global synchronization in your queue, message queue processing. And one of my coworkers in the team, Jim Dinan, with two other folks, wrote a really good paper on this, explaining why this is hard and hard to do in hardware, among other things. And so again, hard to do on a GPU because of the logic. The other thing is MPI supports multiple ranks per GPU. And this makes a lot of sense, and I use it all the time in physics codes. But it greatly increases the complexity. So if you look at Nickel and NVSHMEM both don't support multiple ranks or PEs per GPU, and that means that things are a lot simpler for the implementation. And in most cases, users don't mind, but it's something that is a restriction. So Nickel has none of these things. MPI4 allows you to turn some of them off, but I asked, and nobody's optimized for them yet. So we're still sort of in theoretical land with MPI for these optimizations. The other thing is that Nickel supports multiple ranks or GPUs per process, and MPI doesn't allow you to do that, although I'll propose it for MPI 6. And some AI workloads like this. We have customers who will say, you know what, I do not want to do multiprocessing on my my CPU workload because I'm doing this gigantic data analysis file read thing, and I don't feel like doing MPI parallelism or whatever on that. I just want to do that all in shared memory with threads, but I'm going to have the GPUs act like independent endpoints in communication. And so Nickel does support that. And so these are some of the more interesting differences why the feature set of MPI and Nickel don't perfectly line up. And I think actually the last one is probably underappreciated, that the AI community just wasn't really interested in having to go all in with MPI run launching if they were running on a workstation. And Nickel doesn't require you to do any of that if you don't want to. All right. So now I'm going to switch gears. That was all context. And now I'm going to describe a benchmark, and I'm going to show you a lot of code and a lot of performance measurements. And hopefully all the things I described conceptually will start to fall out looking at the code and looking at the performance. So I'm going to focus on matrix transpose. I happen to like it a lot. I think it's cute and fun. It also relates to a lot of things I've done in science with tensor operations and quantum chemistry, and it also generates an all-to-all communication pattern. So this is of course the trivial version, just to show you, obviously. And this animation, by the way, Cursor made this. I actually didn't do this. I just told Cursor to make me this animation. It did a good job with it. So what I'm going to do in this benchmark, this is this single process version. I'm going to do an accumulating transpose. So I'm going to take Bij and add Iji to it. And then the other thing I'm going to do, which is a little bit different, which isn't transpose, is I'm going to increment the A matrix, the input matrix, every time. And the reason we do this in this benchmark is for verification, because if you do transpose twice, you get back what you started with, and it makes it really hard to be absolutely certain that you did everything correctly. If whatever you did wrong is invertible, you won't know it. And so we've learned the hard way over the years to add this extra work in transpose so that we can always do element-wise verification. And I will say I really do appreciate this, because I didn't write the code correctly in all cases the first time with NVSHMEM, and it's a lot easier to see when you can do this. So this is a matrix transpose. You can go through it a bunch of different ways, column-wise, row-wise, blocks, everything. But this is what we're going to be doing, obviously, on a very big matrix. So I'm not going to focus on the GPU implementation of matrix transpose. Mark Harris wrote a beautiful blog post, I think 2017 maybe, in which he describes the right way to do matrix transpose on a GPU in contrast to the wrong way. And it has to do, you use shared memory and do coalescing and the like. So all I'm going to tell you is that I implemented all of Mark Harris's versions and confirmed that there is a bad version that gets 500 gigabytes a second or less. And there is a good version which gets 3 terabytes a second on an H100. You can read my code on GitHub if you want to confirm this and look at the blog too. So the important part of this is I'm going to use a matrix transpose kernel on the GPU for each GPU operation that gets 3 terabytes a second. And therefore, when you see it, you should expect, 8 GPUs, 24 terabytes a second is what we're going to get as the peak throughput for the single process execution. So that's all I'm going to say. You can read all the details on GitHub, but now we consider this a black box. So distributed transpose. So a long time ago, when I was in another role, me and some friends wrote a paper on basically all the different ways to do distributed memory matrix transpose, and we ran it on strong scaled it from 1 CPU up to multiple cabinets of a Cray supercomputer at NERSC. And, we learned a lot of things and saw some interesting stuff. And so we have an MPI version, a whole bunch of MPI versions and a HMEM version. And so we had some expectations, or I had some expectations about the behavior on GPUs from having benchmarked this before in a CPU context. So if you want to know about a little bit more about the benchmark or the project I'm building this off of, you can check out the links. The important thing is, if you're waiting for where all this stuff is, it's in the lower left GitHub link, Parez kernels, which we call the PRKs. This has absolutely everything. All the code I ran in this is there. It's almost trivial to build it. And if you want the scripts, I can send scripts to reproduce it later. So I'm going to run a whole bunch of experiments kind of like this and try to learn stuff from it. So when we think about the distributed part of this, we're going to have 8 GPUs. So I made 8 columns, and this is not element columns. Think of this as blocks, right? Each one of these squares is, whatever, a 1024 by 1024 block of elements. And we can think of each column as owned by a different GPU. And when the transpose is going to occur, you're going to have to take those blocks and scatter them to all of the other GPUs. So if your GPU 0, you'll have 8 blocks, and you'll send 7 of those blocks to the other processes 1 through 7, and everyone will do this. And so everyone is doing a scatter, which is equivalent to an all-to-all pattern, although you can implement it a whole bunch of different ways. So now I'm going to do that. But this is what's going to happen. We're going to generate all-to-all communication by having every single GPU send data to every other GPU. And then they're going to do the local transposition and the local update. And then we're going to just keep going and measure the performance of this. So I ran everything onto DGX H100 in the basement of the Helsinki office because I can sudo there and do whatever I want. And you can read more about the hardware. The important part of this, we have 8 H100 GPUs, and then we have a pretty large NVLink switch, or multiple switches, but it looks like one, obviously. You can read more about it at Hot Chips in the link below. The important numbers here are the local memory bandwidth of this system is about 24 terabytes. I mean, it's 26.8, but I like numbers that are nice and round. So 24 is my goal. And obviously 3.6 terabytes peak bisection for the switch, which I'm going to round down to 3 and say that's when I do the all-to-all, I can probably get 3 terabytes a second through that switch. And so I know, first of all, there's a ratio of 8, though, so that's a nice number. But these are my sort of loose upper bounds on what I'm going to expect. I want to see 24 terabytes a second in local ops and 3 terabytes a second in network ops. And when I combine the two, I'm going to get somewhere in between. That's the performance goal, and we'll see how it goes. So I'm going to show the MPI version first, just to make sure you sort of settle in before I throw GPU stuff into the mix. Again, like I said, so each GPU has one of these column blocks, and we're going to do an all-to-all. This is just a wrapper around MPI all-to-all. Think of it the same way. The only difference is I do type inference and assume COM world because I'm lazy, and it's a benchmark. So I'm going to transpose this column block into a temporary that is now a row block. And then I'm going to go over all the blocks in the row, and I'm going to do the local transpose, and then I'm going to increment everything. So this is 3 steps, all to all, then I'm going to transpose the blocks, and then do the increment. So 3 steps separate in the all to all version, and then they'll get fused later. We'll see that in just a second. So the point-to-point version of this is this is sort of an interesting one. So in the beginning, I said that one of the powerful things about MPI is just exposing the high-level primitive of the collective and not telling the user to do it themselves. And so this is actually a version where the user, me, tries to do it himself. And there's a reason we have this algorithm in our implementation. One is it reduces the temporary space, which I don't think really matters. And the other thing is you are now interleaving communication and computation. You're not overlapping them, but you're interleaving them. So if you look at the previous version, all to all, everyone blasts the network, and then everyone does something local, and everyone does something local. So you're going to hit the saturation point on the network, and then go to the next 2 steps. Whereas in this case, because you're doing send-receive between pairs and transpose, it's possible that when some pairs are doing send-receive between each other, somebody else can be doing a transpose locally, and therefore we can get, we're going to hit the speed of light on the switch and then not go any faster. So maybe don't flood the network. So this is sort of user managed flow control. There's fancier ways to do this. I could have done a lot more interesting, tricky stuff, but the goal isn't to do everything possible that's tricky. It's just to show the concept of interleaving. So the other thing we do here is we do circulant shift to avoid the hotspot, so we don't have all the GPUs communicate with 0 and then 1 and then 2, etc. Transpose the block one at a time and then increment. Okay, so the OpenSHMEM version, and I like Get. There's a reason. It doesn't matter. It's just because I've been writing Get instead of Put for a long time. And Put is sometimes better. Get is sometimes easier. So I'm going to show a lot of Get stuff. I didn't have time to finish all the Put implementations that I wanted, but it's a great idea to play with that. And what you'll see in the MOE stuff is that they use Put, and you can read how they do it elsewhere. So in the Get version, it's pretty straightforward. You just get the block and transpose it. So it's basically the same pattern, except you're doing a get rather than a send-receive pair. And so you can do the get regardless of what the other process is doing. So potentially the other process might be doing some local compute, and you can pull data from it and then do your local compute. And so maybe this will perform better in some cases. The other thing here you'll notice is that I had to add these 2 barriers. And this is that whole thing about separating versus combining synchronization and data movement, is because Get doesn't synchronize, there is absolutely nothing in this program in the communication data movement steps that will stop these processes from running over each other. And so we have to make sure that we don't update A until everyone has fetched A, and that we don't transpose or pull data into A until everyone has done their updates. So you could do this stuff more point-wise, but at least it's in a relatively well-behaved program that runs without too much load imbalance. Doing a barrier isn't killer. If you have a load imbalanced algorithm, you do not want to do barrier. You want to do this all with point-wise synchronization. In NVSHMEM and SHMEM, it's called put with notification. All the MOE apps use it, and you should learn more about that. But that wasn't in the first hour of what I was ready to talk about. All right, now it's time to switch to GPU versions. So the nickel all-to-all version, and I'll show you why it's in quotes. This one looks exactly like the MPI version, except for the GPU part. So I'm going to show two versions. One is bulk and not. And so this not bulk version is the first one I wrote, and it just does exactly the same thing as the MPI version. The difference here is, unlike a CPU where function call overhead is basically nothing, I'm firing off a whole bunch of different CUDA kernels, and it's better not to. So I wrote a bulk version which goes and iterates, does all the block iteration on the GPU using the Z dimension. And now I have one kernel launch. It's a little bit faster, but it's mostly invisible, especially for large problems. Lastly, same thing. I do a CUDA kernel to increment everything. So this is 1-to-1 with the MPI version. And just for reference, so I did nickel all-to-all myself because we don't have the all-to-all function call in there yet. But nickel is designed to do all-to-all with Send-Recv. So you just create a group, you put all the Send-Recvs into it, and then end the group, and this goes onto the stream. And so you can look at the nickel docs. They'll show exactly this pattern. I just copied it and put my cube wrapper around it. So I'm doing a nickel all-to-all here on a stream as just implicit stream argument. So what we see here is we get a slight bump from the bulk as expected, and the approximate performance is 7.5 terabytes a second of throughput, which is neither 3 nor 24. So I broke it down. I ran the CUDA event profiling to get it through. And what you see here is when you're doing the all-to-all, you're running at about 2.7 terabytes a second, which is close to 3. And when you were doing the local part, you're getting about 23 terabytes a second, which is close to 24. So this is right in line with my expectations. So the reason you get 7.5 is because some of the time you're at 23 and some of the time you're at 2.7. And you can't average the bandwidth. You have to look at the time and then invert it and all that. But you can see this from the time breakdowns that things make sense. You're bottlenecked now by going through the switch, as you would expect from basically all performance models of distributed memory. Now I wrote the nickel Send-Recv version, and this one's interesting because this was a bad idea, and we'll see this in just a second. So I'm attempting here then to do my own user level flow control on Send-Recv and be cute, and it turns out this is bad, and this is an important thing to understand why this is bad. So you see these stair steps here where the point-to-point version that does pairwise isn't anywhere near as good as just dumping them all into the network at once. And the reason is that nickel Send-Recv is designed for developing custom collectives. And essentially all of those use cases involve more than one Send-Recv pair. And so nickel says, I think you're probably going to be writing your own all-to-all, your own gather V, etc. I'm not going to blow everything in the network as fast as possible because that might, overwhelm the network and end up being slower than throttling it. So nickel is sort of fighting with my attempt to be nice to it by using its own. It was going to be nice to me, and now we're both sad. The good news is that you can work around this. So you can use multiple streams, and basically, nickel will then not apply this logic. And if you are interested more in this, my coworker Josh Romero has this CUD comp library that does a whole bunch of auto-tuning, optimal scheduling tricks for the all-to-all pattern in a 3D like 3D FFT type problem, and you can read the code online. And Josh was telling me, oh yeah, you can do all these different tricks to get this to go away. And I learned that on Thursday night, so I didn't have time to redo everything. Okay, so now I'm going to do NVSHMEM, and I'm going to start with all just to show that it's the same. One thing that's interesting is if you are an MPI programmer and you go and use SHMEM or NVSHMEM, you need to know that all doesn't mean the exact same thing. So in SHMEM, they are trying to avoid synchronization at all costs. And the all-to-all primitive in SHMEM and NVSHMEM is assumed to be implemented as everybody does a put to all. Okay, so one-sided scatter. And what that means is it will not wait until the target is ready. It'll just write to it. There's no synchronization involved there. So you have to put a barrier in front of it to make sure that you don't blow over something that was in the middle of being updated locally, as the pattern of my algorithm requires. Same pattern as before. We have the bulk transpose, the not bulk transpose, and the local increment. So now we see here all-to-all is about the same. So, and I apologize, nothing interesting has happened yet, but I promise it gets interesting in just a second. NVSHMEM wins by a little bit. I haven't looked at the source code enough to figure out exactly what protocol switch is going on, but NVSHMEM has been optimized much more heavily for latency, which is why the smaller cases are more different. Obviously, asymptotically, they're both identical. So the one-sided get implementation is a little bit more complicated. And I will say I wrote this one second after the one I'll show you later, but I'm doing this in order. So there are two versions of get here. So the first one looks a lot like the code we've seen before, with a loop over blocks, doing a get, doing a local, and then the barriers, and then doing with the increment in between. But because this is NVSHMEM and I can do device-initiated communication, I can take this entire thing, this loop over blocks and the get and the transpose, and shove it all inside of one CUDA kernel and fire that thing off on the device and let it run. The bad news is I sort of ran out of time and didn't do all the bookkeeping. So I did something that I discourage people from doing. But hopefully you can learn from my error. It's not the worst thing in the world, but it's not the best. So you can do a block and a warp-wise get, and I should be doing that, but I didn't because I was trying to get this in real fast. And so what you see here is I basically put an element-wise get operation into the place where I normally would have just done a load. So replacing a load or an equals sign with essentially a mem copy adds a little bit of overhead, although this will get inlined, and on NVLink it'll get inlined and mapped to a store, but there will be some logic that shows up in this kernel that didn't show up in the load version. And so this isn't perfect. So note to everybody, don't use element-wise gets inside of your kernels unless that's your pattern. Amortize everything, do a whole bunch of arithmetic. But we'll see later. This is not actually the best way to do this. I'm going to show you the good version that was actually the goal here all along. But you can, if you want, and you can see examples of it online, both in our docs and in Perplexity's benchmark, of using fine-grained communication and fine-grained synchronization on the device in an MOE, and that's absolutely the right way to use this stuff. But this is just here as a reference to compare it to the load store version. I'm going to show the pointer version. NVSHMEM pointer version. I'm going to show you in just a second. The other thing is that because I'm on an NVLink domain, this get isn't so bad. It's going to map to an NVLink load. If this is going over the network, this is going to be not the best way to do things at all. And if you're going to do NVSHMEM across the network, you want to be smart about how many GPU threads you actually have touching the network. And you'll see in the MOE folks, they do that stuff smartly, and the docs describe it in more detail. So this is the one that I wanted to show, and this is the exciting one. This is exciting because NVLink is cool, but it's super exciting because NVLink is a lot bigger than a node now. So I ran this on an NVLink 8 domain in a DGX box, but we are shipping NVL72s that have obviously a whole lot of GPUs in them connected by a single NVLink switch domain that allows this to be indexing the whole rack. And that's what I'm trying to demonstrate here. So in this case, I start with the version that I had before, where I was going to do, blockwise communication, except the block communication now is replaced with NVSHMEM pointer. And all that does is say, what is the remote address of the start of the block that I was going to get with communication, make a pointer out of it, and give it to the kernel. So there's no communication happening here. This is just lookup. And then it gives this remote pointer to the local compute kernel, and the magic of NVLink takes care of it. Of course, I can do the same thing in the big fat kernel model, which is what I'm going to do here. So this is the one that's going to be really cool because I'm basically going to call one CUDA kernel, and it's going to, inside of it, go over all the blocks, look up all the pointers, and do everything as if it was local memory. So there's a intermediate kernel that you don't see. You can look it up. It's just the loop over blocks part. But what you see here is that for each one of these blocks, you grab the pointer and then do the device side call of the optimized kernel, and then sync memory so you don't blast SLM. And then you just go. So you basically now have eliminated communication from your code. There are no send receives, there are no all the alls, there are no puts, no gets. There is the barrier that you'll do later, but this is nothing more than give me a remote pointer address. So now we look at this. So remember, 7.5 terabytes was our standard number, and the Git version for the small problem sizes ramps a little bit faster, but in general, it's about the same as all and point to point. On the other hand, if we do this with a pointer, direct local access or direct remote access, we're now 30% faster. So we're at 9.5 terabytes a second. So what this means is we were able to improve the communication efficiency an enormous amount, while also making the code a heck of a lot simpler because there's no communication. It's just NVLink, do your thing, and calling local compute. So I think this is super neat. It's kind of like if you're old school and you remember Cray X1E or other fun supercomputers where you could do this. This is kind of a magical thing, and it's even crazier that you can do this over 72 GPUs on one of those racks. But this is a significant performance difference to take advantage of NVLink and remove this separation of communication computation. So I should emphasize that the the NVSHMEM pointer access version only works with an NVLink domain. So I asked Cursor to draw me a picture of this, and this is what it came up with, which was a heck of a lot faster than the PowerPoint drawing I would have made, but maybe not the most beautiful. But the point of this is you can have multiple NVLink domains, and between those NVLink domains, you can use NVSHMEM put and get. But within those domains, you can use pointer access. So, and this is actually why folks in MOE space will do this. They'll use NVSHMEM because it's portable across this whole domain, whether you've got IB or NVLink. But it gives you this immediate way to take advantage of NVLink as a load store network and eliminate explicit communication. And NVSHMEM is basically the only model out there that can do anything like this. You can do the NVLink domain part with CUDA IPC if you want. It's a little bit more complicated. Most people figure it out, but it's complicated. But if you really want to combine the two, it's very, very difficult. All right, so just to summarize, this is absolutely everything all on the same thing. Here's our direct access. Here's our everybody doing a pretty good job with all, and here's our unfortunate throttling situation, which we know is solvable, but happens if you can be surprised by this if you don't know what's actually going to happen behind the scenes. and then you have to go mitigate it. So in general, don't try to be too smart. Just write all-to-all, and all-to-all will do about what you'd expect to do. It'll saturate the network, and then it'll do local stuff. Whereas when you fuse that network step into the compute, you get a pretty significant benefit. Okay, I'll pause here because there might be lots of questions about the experiments. Maybe.
All right, Mateo, you want to go first?
You can go now. I need to draw my thoughts.
All right. So one question I had, like, while you were coding all this stuff up, is it wasn't too clear to me how to think about the programming model of like SHMEM versus like the regular sort of memory hierarchy. So is it sort of like when you sort of do gets and puts, like those can again be in arbitrary locations in memory? Can you say, I want this, I want to get, for example, this location in shared memory? Or is it basically you just say, I want some memory, and then it's up to like the other GPU to figure out like what memory to give you exactly?
Well, so the SHMEM concept, the symmetric heap, everybody takes the same size slab and contributes it. And when you initiate communication, you are in control. So NVSHMEM will make it so you don't have, if you do an NVSHMEM put or a get, you don't have to think. You can do a put to PE myself and just load it out of your own memory. You can do a put and a get to another GPU, which is NVLink connected, and it'll also be load store. And NVSHMEM will basically go in and do some pointer arithmetic to give you your virtual address view of the other GPU's memory, which might have a different address in their thing. It's, one of these, it's two different virtual address maps that point to the same thing. NVSHMEM will also go in and determine, oh, this is outside of an NVLink domain, and therefore I need to do the right network operation, which that's a lot more complicated and goes through a couple different code paths, sometimes involving the host. But NVSHMEM really hides all that, and it's just saying, as long as you know which GPU you want to talk to, you can go talk to it. However, if you're smart, you will actually want to sort of hoist this logic into your program. So what you can do, and I don't do it in a hybrid way, but I show both versions. If you call NVSHMEM pointer on a segment of memory at a remote PE, if it returns to you a valid address, that means you can load it. If it returns to you a null pointer, that means you can't load it. So if you want to be really tricky, what you'll do, really smart, is you'll try the NVSHMEM pointer, and then say, if not null, do it as if it's local. Else, issue the put or the get, and then let the network take care of it. And understanding that there's going to be a performance difference between an NVLink load and a network read or write is important if you really want to tune for peak performance. But you can start with it just works, and then you can do a hierarchical optimization for, think of it like NUMA or whatever, or intranode, internode. But the good news is when you go across that network domain, you never need to think about what network you're using. And I think that's one of the really important things that NVSHMEM is doing.
Right. So I have a longer question by Arun Demir. So I'm just gonna put it. I'm gonna read it. I don't know if can you see it?
No, I'll switch. I'll switch. Yeah. So what I mean is, some networks, Blue Gene was such a network, you could basically just spam the network, and there would be no real punishment for it. I mean, the data would move as fast as it could move, but you wouldn't have some sort of degradation by saying, I'm going to give you all of my messages all at once. They would just go through in the order that they got in. Some networks, most networks, in fact, if you have a queue and you inject like 1 million messages into the queue, the queue will run slower than if you only inject 100 messages at a time. So there's a common trick when you do collectives in all-to-all of doing some sort of windowing where you say, I'm not going to just go for all 1 to n send. I'm going to do for 1 to batch, send, wait, 1 to batch, or whatever. You batch it through, right? And so what I'm doing with the pairwise exchange is I'm saying I'm going to batch it 1 big message at a time, because I know that I can't move through the network faster than the data moves. Why should I pump more into the queue? And what we're learning in this scenario is that Nickel is actually smart enough to do that. When you give it that group, Nickel goes in and says, okay, I'm not going to go dump all this stuff into the network all at once. I'm going to schedule it intelligently, because it's expecting me, if I do 1 group on 1 stream with Send-Recvs, it's expecting that I'm writing a collective. So Nickel's helping me, but when I try to help Nickel, it's a negative interference. So there's a workaround, but this is basically the Nickel has this logic in the Send-Recv itself, and this is not true of MPI. So I know of no MPI implementation where we're doing a whole bunch of Send-Recvs will trigger a flow control. If you want that flow control, you call all-to-all, and it's built in. That's why you call all-to-all. But if you want to spam the network, you can do that with MPI Send-Recv. And so this was sort of counterintuitive for me, but now I know.
I have another question from Arun.
Yes, this is a great question. So we know of some users of NVSHMEM who use NVSHMEM strictly for allocating NVLink pointers, because you do NVSHMEM init, then you do NVSHMEM malloc, and the pointer you get back from NVSHMEM malloc has all of the NVLink, address mapping. It has, all the IPC stuff. It has, if you have NVLink sharp, it'll also do all those mappings. Basically, it's a universal malloc for all the GPU networking goodies. So some people literally just call NVSHMEM malloc for that purpose, and they don't actually use NVSHMEM communication at all. They just do load store with everything. So this is a good observation. NVSHMEM is a very nice convenience function for all that capability. On the other hand, some people say, no, I'd really like to write all the CUDA to set all that up because I don't want a dependency. And I've seen both, and it just really depends on what users want to do.
All right, I have another question. This is a 2-part question from Angelo. You stated comms are eliminated, and then the second part is I'm
not sure. I thought I said NVSHMEM comms were eliminated when I switched to pointer, but maybe I misspoke. Can we come back to that one and maybe I'll remember what I said wrong.
All right. I guess, Mate, any other question, or should we keep going?
Yeah, I have a rather random question. You had a graph on like the first, second, or third slide of the second part, like comparing all the methods of matrix transpose on different. It's like a rather old slide. No. It was like on different scales.
The Cray numbers.
Yeah, exactly.
There we go. Yeah.
I was wondering, like, you can see that here, like, SHMEM actually scales very poorly with like the number of cores. Like, why is that? Like, is it because of the lack of synchronization, the network?
No. So SHMEM is doing a fantastic job here up until, and this is when I give the talk on this stuff, I explain this. It's because at 1536 cores, the message size is at, I think it's about 4K. And 4K is that everything above 4K is pretty efficient in an RDMA network. Once you drop below 4K, it gets less efficient. And so what happens at 1536 is that all of the models that are doing one communicating endpoint per core start to get into the small message regime where the network's less efficient. So at 12, I can't remember, it used to be on the slide, but at 12,288, it's like 64 bytes or less per message. Okay, that's too small to hit line rate or whatever. What you see in the MPI curves that go up, those are all hybrid, meaning MPI is going to do one MPI process per node or per socket and do threads within it. And so the communication volume is the same, but the message size is much larger. So MPI keeps going because it's still communicating kilobyte messages. And this is just sort of an artifact of messaging stacks and networks and CPU domain decomposition. We don't see this. Well, you could see this in a GPU. That's why when we look at the NVSHMEM and we have block and warp and thread, right? You really would like to do a block put if you can do the arithmetic and get it done, because then everybody's working together. If you do a warp, well, that's still good. You get coalescing. If you get thread put, then every single thread is sending a single piece of the message, and you're not getting that coalescing behavior. You're not getting the networking aggregation. So this phenomenon will show up in NVSHMEM, but I just don't have the example for it yet. Sorry.
Yeah, thank you. I also have one question, to circle back to Nickel. And you said that Nickel chooses the algorithm or the protocol for you based on the message size, the architecture, and so on. Is there a way to actually tweak those? Like, for example, say that I want to go with the memory, the bandwidth oriented protocol.
Yes. Yes, we do. And they're all attributes in the communicator object, and there are some environment variables as well. However, my team, when I said I have in there the phrase trust Nickel, they said, yes, please tell everyone to trust Nickel and don't try to tune it yourself, because we do have a whole bunch of tuning options. But the whole point of our team that does a whole lot of work on this is to make sure that most people shouldn't have to do that. So I'm going to tell you that they exist, and there is an NVIDIA developer blog by some of my colleagues about tuning Nickel that was written in the last month. But I'm also going to say, please don't read it. I mean, unless you have a really good reason, because Nickel is going to try very hard to do the best protocol choices for everything. And if you start making those yourself, you might find that on one system for one application for one job size, you're going to win. But now you're going to go into non-portable hell where you have to go retune and rediscover all the right whistles for every use case. And then you might be sad. You might say, well, Nickel's slow. Well, it's slow because you changed the default and didn't let it make the right choice on a new machine. So yes, we have them. But use them as a means of last resort.
I think we should get going. We might need to batch some questions near the end, because there's a lot more questions in chat for what it's worth. But I'm really sorry. If you want us to ask a question, just ask it again near the end. Apologies.
All right. So now I'm going to bring this all together with the stuff that really matters in AI workloads. So this is taken directly out of the Perplexity blog. Please read their blog. They did a great job explaining this stuff. I talked to these folks. It's great writing. Really nice benchmark that, once you get your head around it, you can learn a lot from. So this is expert parallelism. So you have, multiple requests to different GPUs coming in, and when they hit the router, it's going to then scatter, some of these tokens to other GPUs. Obviously, this is just two, but there may be more. MOE domains are getting bigger. And that's going to be an all-to-all pattern. And it's actually going to be an unstructured all-to-all pattern, which is why, even though you see all-to-all and you'll see send, it's all done with NVSHMEM put. because the router knows where this stuff is going, and it knows what memory it's allowed to write into on the other GPUs. But the other GPUs don't know what's coming in until it lands, and then they go look and see, oh, I've got some tokens I need to chew on for a bit. So if you look at the code, you'll see this dispatch and combine, where you have a whole bunch of things happening. You have a dispatch send step. Everybody does this, and then you have the receive. This is implemented with put notifier. There's a counter. I think you just increment the counter. And then there's the other part of this, which is the combine, where you do the same thing in reverse, and then you do some summation. And this is all written with on-device NVSHMEM, so that the router doesn't have to return a bunch of metadata and then have the CPU kick off some comm ops. It just says, I'm the router. I know where things are going. I have the data. I'm going to send it into the network or NVLink, and then we go. And then the synchronization is carefully managed to look at this stuff when, and there is a barrier at the end, but there's a whole bunch of things that don't have a barrier in them. And this is, of course, the real punchline. If you look at this, I don't know what the original implementations that they did with all looked like. I haven't read that code, but you can see obviously the bar size is pretty significantly different. And what they've got in their fine-grained NVSHMEM version of this is significantly lower performance. Obviously, there's two different IB protocols. And one of the things that they do, and they explain this more in the blog, so DPP actually is a little bit faster. And this is a fascinating story. I'll just summarize briefly. So the folks at DeepSeek did some very specialized hacking of NVSHMEM on IB because they had a very special use case. They knew they were only using IB, and they knew they were not going to require some of the things that NVSHMEM was going to do for them. And so they punched through and cut out a very small amount of synchronization that made a really big difference. But Perplexity, because they run on IB and on AWS EFA, they were not willing to make these assumptions. So they published these IB numbers for direct comparison, but they say in the blog that they care about portability to other networks. And so they stuck with the NVSHMEM, public API. It didn't do those fancy tricks so that they would be able to get almost as good performance, but be able to do it in any cloud they want to run in. And there is some stuff coming in the future which will, I believe, allow the DPP trick to be done without doing the really creative hacking that DeepSeek did. But this is obviously, if you look at the numbers, this is at least a 10x performance improvement relative to what they were doing before on MOE, and that's a big deal. If you're like me and you type Perplexity queries all day long trying to learn stuff, you want the latency of those tokens to be 10x better if you can do it. So lastly, so this is the roadmap, and this is an important thing, because I talked about why NVSHMEM had all these cool features in it. I didn't say that they were in nickel, and that might make people say, oh boy, what should I stop using nickel and start using NVSHMEM because I'm doing MOE? And it turns out no. So we have already rolled out support for symmetric memory, which is the first step in doing the NVLink thing that I described, with remote pointers. And this GitHub preview went online yesterday. I saw it a couple hours after the announcement for my talk went out, and I haven't had time to read the code because it's been my weekend. But the device API is in that version, or is a preview, and then multi-node NVLink symmetric, and then you see here on the next version after that, doing put and get from the host. So we're learning from NVSHMEM, which pioneered the on-device communication, but we know that there's a bunch of reasons why folks want to be able to do that stuff from nickel as well. Either they're already using nickel, or they want to use some features that nickel has that NVSHMEM doesn't, which I didn't get into here, but there are some. So now you can do this. So what this really means is, with Nickel getting some of this one-sided and symmetric support, you're free to choose one or the other. We obviously care deeply about both and continue to develop both of them. And NVSHMEM has all the collectives and on-stream and whatnot as well. So if you like NVSHMEM, you can use it. And if you like Nickel, you can use it and do essentially the same things in both of them. So the feature parity is essentially going to close, and then it becomes more about sort of some of the nuanced differences in the runtimes and ecosystem, if you're already using Nickel or NVSHMEM. So this is the very end. So just to summarize, NVLink with NVSHMEM today is easy, fast, and you get portability on the network part. And this is really neat. So the easy part is it's just a pointer. Use NVLink. You don't have to care. Let the memory controller take care of the magic. It's fast. As you can see, I was able to fuse the communication into the compute and get something like a 30% bandwidth improvement with code that's actually easier and simpler to write. And then, as Perplexity demonstrated, you can mix and match these things, and you can get put and get working on different networks as well as NVLink. And so you can write one version of the code and scale it across. And then if you want to specialize, as I said before, you can do the pointer. You can look for a pointer and try to use it if you can. Otherwise, let the network do its thing. Nickel, of course, as I mentioned, the roadmap will bring in this NVLink stuff this year and add on to, of course, all the existing stuff, which is all the collectives at scale and all the support for AI workflows and some of the elasticity and RAS stuff that folks need, that is really important for AI and less so for HPC. As I noted, we belabored a little bit, but trusting Nickel, not trying to outsmart it with protocols, because it's gonna do that for you. And then, please, check out the preview that went online yesterday and look for all the symmetric and device stuff that's coming down the line, that will hopefully make it possible to do all the neat device initiated tricks with Nickel. So that's it.
Sweet. Thank you so much, Jeff. I guess, yeah, like we have a bunch more questions. Maybe I'll start with one while more people are asking. So like you mentioned how like MOEs are kind of like a nice like sweet spot for NVSHMEM, and I was kind of curious to ask you about like other areas where maybe like the SPMD programming model kind of shows its cracks. I think I'm also asking this because you mentioned the sort of multiple ranks per process, and I'm thinking out loud, like things like post-training, for instance, where you have like, like one process doing inference, another one like holding a copy of a cache, another one doing training. Do you still foresee like NVSHMEM being like useful in this setting, or is it like you just need a completely different set of libraries to use?
No, so this is one of the key motivations for bringing this feature set into NVSHMEM. So NVSHMEM, we have done the creative design and how to map it onto the GPU, but that API is the OpenSHMEM API, and the concept of the symmetric heap is both powerful and restrictive. So if you go all the way back to the beginning, this philosophy of SHMEM is, if it's not fast, don't do it. And that's a really great philosophy. It's how CUDA started. I mean, back in the good old day, right? You couldn't do much with CUDA, but what you could do with CUDA would be blazingly fast. And then CUDA has gotten more expansive, right? So fast or nothing is a great philosophy. But what it means is NVSHMEM's notion of the world, right? Those processing elements, there are n processing elements. They all run together. They all do collective memory allocation, and they do collective synchronization. You can create teams, but you cannot get away from the worldwide collective memory allocation. And what this means is, if you want to write a heterogeneous application, you just can't have some of your processes allocating memory and some of them allocating or not allocating, or allocating a different size of memory. That symmetry is what makes all the logic inside of the communication lookups order one. It's super beautiful. But that rigidity means that heterogeneous like application building is complicated. Now, some of the cloud people can figure out how to do this, and you can do out of band, you could do NVSHMEM cliques that are separate from one another and wire them together with some other communication if you want. But that's just something that, adds more work on the user. Nickel obviously has the MPI communicator concept. And one of the things, if you look at the symmetric stuff, it's like, well, wasn't it easy? Well, no, it was actually quite difficult to design it because we had to go through the design phase, just like MPI did, of how are we going to build this one-sided shared memory or shared address concept in a communicator world so that we can have one communicator and two communicators, and maybe they overlap, maybe they're disjoint, but they need to be able to do their own symmetric memory and their own one-sided. And that's a lot more arithmetic inside of the runtime. You want to do it efficiently. So if you want to compose one of these heterogeneous workflows, as people do with Nickel, where you have different levels of parallelism, tensor and data and all that, Nickel is designed to let you do that. And now when we bring in the symmetric and device stuff into Nickel, you'll be able to bolt that on where you want to bolt it on, but not necessarily use it across the whole domain. So it's a great question. And NVSHMEM is awesome, but really quite restrictive in ways that we wanted to get out of.
I see a few more questions, so I'm just gonna go through them. So from Angelo, I think, yeah, can you see the screen?
Set up. Well, yeah, I mean, everything is sensitive to bandwidth, right? So if you go through PCIe, it's 50, and if you go through NVLink, it's 450, and if you go through HBM, it's 3000, right? We were talking about this the other night when I went through the talk, and those are the magic numbers, right? Those are different by almost an order of magnitude, and you absolutely see that. So I showed everything within NVLink domain, and I get NVLink domain performance. The moment if I did the same thing, and the moment that I went over 2 nodes with IB, I would now, if I'm running over 8 rails of IB, I'll get pretty nice bandwidth, but it won't be the same as NVLink. So you really have to think carefully about this, with your performance expectations. You're rate limited by the slowest step or whatever the rate limiting step in the network. But this is where the hardware comes into play. The reason NVLink domains are scaling up is because you want to scale that type of bandwidth to a much larger domain, because obviously as these experts get bigger, as the tensors get bigger, you need to have the NVLink bandwidth property within that to do some of this stuff. So we do our best to keep up with the hardware, but the hardware will ultimately be limiting. You can also think about the algorithms, right? If you can keep your tensor parallelism within an NVLink domain, that's a good idea. And then you could do something that's maybe a little less communication intensive between those domains. And of course, that's some of what MOE is about, right? Is about chopping up one big MLP into multiple MLPs that don't talk to each other as much. So it's part of the application design as well to figure out where the bottlenecks are and not hit them as hard as possible.
Another question is here from Lucas.
I haven't done it, but I would expect it to be really, really good. And the reason is, and maybe I'll ask Marcus and Jerry, who worked on that tutorial as well, to update this for next time. One of the things that's kind of nasty about a stencil halo exchange, right, is you have this square, and one of those dimensions in memory is contiguous, and the other isn't. And so when you go down that non-contiguous thing, you're going to send basically one element of the halo one by one all the way down, because they're 1,000 elements apart. And obviously that doing that with communication, calling even NVSHMEM put as low latency as it is for one element at a time going down the line, isn't going to be as nice as if you just hit that with a load store operation, and let basically the warp hide the latency. So I would expect it to be noticeably better if that Halo exchange is the thing that, you know, limits your app.
All right, I think I see one more question, which is here.
So this is the one we talked about with you really can't do a team symmetric heap. I know there was a proposal in OpenSHMEM for that. I don't think it's in the spec yet, but I haven't read the spec in a while. But I think I would have heard about it. And I don't think I saw it in NVSHMEM docs either. So the sort of sub world or sub communicator symmetric heap is really something you'll get from Nickel.
All right, I think that was it for me. Matej, any questions on your end?
Yeah, from me as well.
All right. Hey Jeff, thank you so much for this. This was awesome, by the way, and your slides are awesome and your code is awesome. So it seems like you kind of made, I think, me and probably a lot of other people curious to go dive through the history of a lot of these standards. So thank you for this. This is amazing.
Yeah.
All right. Well, I guess we'll see everyone.